Yeah, thanks.
Give me a message.
Perfect. And then, like we did last week, we're gonna talk about standard errors and test the hypothesis around the coefficients. But then we're gonna introduce this idea about whether or not it's not only statistically significant, whether or not it has any relevant economic magnitude. We're not gonna do this robust standard errors or weighting. I think that's beyond kind of the scope of what we want, but we're gonna introduce this indicator variables around, in our particular case with this Redfin data is where the geographical location of the property is. And in this case, we have the metro area of Washington, DC, Maryland, and Virginia, because the DC area kind of spans those, and show what those mean and how to interpret them in the same way that we do the coefficients and the regression on statistical significance and things like that. So just as a refresher, this is the regression model that we had last week. And we had the home price being this dependent variable, and they had a linear relationship between it and which had this coefficient m, and then x in our initial case was we at the end we did distance from the metro area, and then there's an intercept term. And what we did when we did that, we found that things didn't look really that good. So let me just kind of bounce back to that and show you kind of what we meant by that. So, and this was the problem that you did at the very end of class, where we are in this line 70 and 71. We ran this regression of prices against metro distance. And so let me go ahead and run that. And then let me go ahead and report those results. And that's down here at the bottom. And so you can see that the only thing that's significant here is the intercept term, and that the metro distance is not significantly different from 0, because its t-value is not, in absolute value, not close to 2, and hence you don't have any stars out here to denote what its significance level is. And so really this isn't a meaningful regression. It just doesn't have anything that is interpreting the change in price relative to the metro. So instead of doing that, an alternative regression would be to regress the price per square foot on the metro distance. And so let's go ahead and do that. And so that's what I do here. I'm going to filter it by throwing away that missing observation. And once I do that, then I'm going to go ahead and on line 84, regress the price per square foot on the metro distance. And let me do that, and then I'll produce the results and show you what it looks like. And there you go. Down here in the bottom. So, bring that up for my benefit, not for your benefit, because you can probably see that. So, does anyone want to look at that and explain it to me? What we're seeing here with regards to the intercept parameter value, the slope coefficient, and whether or not these things are statistically significant? David, do you have an idea of what's going on there? How would you interpret those?
Yeah, so this is about the housing price, right? The metro distance. So, but this is in terms of price.
This is in terms of price per square feet.
Okay, yeah, so they're saying that regardless of anything, the price is going to start off, I don't know the measurements of this, but around 493,000. And with the metro distance, I'm guessing as you get closer, I mean, as the distance gets further, it decreases.
Say that again for me.
As the distance of the metro gets, well, since it's negative, if it gets further, it will decrease more. Like the more.
Right, so the price per square foot would decline the farther away you are from the metro station, right? The further the home or the apartment or whatever the residence is from that. And it's minus 87, so for every mile, because this is in terms of miles, for every mile away from the metro station, the price per square foot would drop how much?
87,000.
87, and this is in dollars because it's price per square foot.
Oh, $87.
And so it's just $87 because we're thinking about it in that context, okay? So let me see if I can, okay. Kind of jumping up here to this point. So that's what we have right here, to just kind of blow it up bigger, okay? So you can actually see it. Now, Shavai, given what we've heard thus far from Taylor, is the coefficient of 87.38, negative 87.387, what can you tell me about the statistical nature of that number? In other words, is it significantly different from zero?
Yes.
And how are you at, what is in the summary here that helps you make that conclusion?
There's no, well, would it be a star by it if it was?
So here you have 3 stars,
Oh,
right?
I see it. Okay.
And the stars, any star is telling you that it's significant.
Oh, okay. So it is significant at 0? Or
This is always hard to see. So nothing would be not significant. A period would be significant at the 90th percentile, or not, you know, the 90th. And so in that case, your significance level would be 10%. If it's 1 asterisk, it would be 95 or 5%. If it's 2 asterisks, it's 99. So what, you know, 1%. But if it's 3 asterisks like it is here, it's gonna be 99.9 or 0.1%. So this is significant with a significance level of 0.1%. Does that make sense?
yes.
Now, you can see that you have this p-value over here that's essentially 0. So this t-value is way, way, way out into the tail. So there's lots of evidence to reject the null that the coefficient is equal to 0. So in this particular case, you would say that the coefficient is significantly different from 0, and I would reject that it's equal to 0, right?
Yes.
And that's very different than what we found for the relationship between the metro distance in the price of the house. There you saw that it was a minus 24,000. But if you come out here, there's no dots. So we know that it's not significant at either the, 1%, 10%, 5%, 1%, 0.1% level. And you can see that also because the p-value here is bigger than, say 0.1 down here. So nothing here is giving you any type of evidence against the null hypothesis that the metro distance is not a factor in the explaining prices, and so we can't reject that. Here, because we changed it to price per square foot, we're getting a relationship that is saying that no, metro distance is important with regards to explaining the behavior of the average level of the price per square foot. Any ideas, Brianna, why it's working for price per square foot and not for price? Oh, you just went back on mute.
Okay, I'm trying to play with the features with the notes to take notes, but I guess it doesn't let you unmute with your thing. But
Oh,
I'm sorry.
it's
So
okay.
you said what's the difference between price square per unit and price?
That's gonna be part of the answer, but the question really is why are we finding metro distance to be relevant for price per square foot and not relevant for just price of the house? Any
Because
ideas?
yeah, because the closer you are to like a metropolitan area, the likelier it is that the square unit are going to be smaller. The square units are going to be smaller, but the price will still be higher because you're closer to urbanization.
Okay, that's a good hypothesis, and we could work with that. I mean, there's a lot of different ways to provide an answer around this. For me, I
I have another hypothesis.
okay, Taylor.
It's not significant for price because well, I remember we said something about the bedroom. I lost my thought.
It could be just simply that there's not a strong, remember when we plotted that data? Let's just go ahead and plot the data from this is the data. Let's plot that. Oh, why isn't it? Oh, I know. Huh. Oh, I know why. Let me just come down here and I'm gonna just do it this way. There you go. And if I look at that data, you don't really see any kind of linear relationship with it. And so it's not surprising that we're finding that that's the case here, that we're not getting any significance on that linear term. Now let me do that same graph, but I'm going to change price, I'm gonna change the price here to, square feet, price per square feet. And run that again. And plot it. And look at what we find here. Now, I still have this outlier way up here at the top. So the data that we're gonna be working with and that I showed earlier actually deletes that out. But if I just simply look at this area right down here, compared to what we had before, there seems to be a little bit more relationship here between the metro distance and the price per square foot than we saw between the metro distance and price. And it's not big, but at least it's there. And that's why, you know, there's something about the relationship where we're at least getting something with prices where we didn't get anything when we were just looking at, we're getting a relationship with price per square foot where we weren't getting it with regards to just prices. And it may just simply be that the size of the house, you're in an urban area, that means that, you know, you got smaller houses, things like that. So these are all things that you kind of have to run through your head and try to provide some explanations around it so that you can justify why the results make sense. So let's come back to some of these questions that I've already asked, but just to dwell on them a little bit more. We've already asked this, you know, I kind of answered this question, what is the estimate for the relationship between the distance from the metro and the price per square foot? Well, that would be this coefficient right here, this negative 87.387, right? Now, one of the things that also comes up in this is, okay, what does this mean with regards to prediction for, I'm not saying the price per square foot, but I'm saying the expected price per square foot. Any idea why I want to make sure I use the word expected and not say, oh yeah, for this many miles away from the from a home, the price per square foot is equal to whatever the regression says. Why do we want to use the word expected? Any ideas, Taylor?
Because it's still an estimate. This is not like a definite price.
Right, exactly. There's still uncertainty in this thing. There's nothing that says that everything's fit with exact precision. In fact, you can see that here by just looking at these R squares, which is telling you that you're only explaining right around 17% of the data's variation. So there's more than 80% of the data's variation that is not being captured by this regression. And so other things besides metro distance is going to be that are missing from this regression that could help explain more of this. But whatever's left over, we throw into the residual, and we think of this as being the expected price per square foot given a certain, you know, distance from the metro area. Okay, so let me go back and show you the data. Okay. Okay, this is price per square foot, and this is metro distance, meaning how far you are away from the your house is away from the metro stop. Okay, it goes from 0 just a little over 5. So 1, 2, 3, 4, 5 miles away. Now, if you look at this, where are most of the houses that I've got in my data set relative in distance from the metro? Any ideas or guesses or?
It's from 0 to 2 miles.
Yeah, basically, in fact, you get a strong cluster here that are all really between 0 and 1 mile, okay? So when I'm thinking about reporting my results, do you think that this would be, this regression would be a good predictor for a house that's, say, 10 miles away from the metro station?
No.
Do I even have a house that's 10 miles away from the metro station?
No.
No. Now think about it from an economic standpoint. If you live 10 miles away from the closest metro stop, what are you gonna do if you're ever going to use the metro?
Drive.
Yeah. And once you get in your car, you gotta have a reason to get out of that car to get on the train. And because of that, it probably doesn't make sense to come to this regression. Let me put it this way, to come to this equation and stick 10 miles in here. One, because it is not meaningful, and two, the parameter that I've estimated here for M1 for my data didn't even include a house that was 10 miles away from the metro station. So it would really be in making an inference about price per square foot for a metro distance that isn't even being part of the data set. And so inference in there is completely outside the scope of the analysis. And that's where we can kind of see that here. Where would our results be applicable? In other words, which homes or properties do you think that this would be most helpful in predicting the price per square foot?
Homes that are within, well, really within 0 to 2 miles, because around like 3 and 3.
Yeah, I think, Taylor, that's exactly right. Because if I run a regression through here, I'm going to get a line that really matches up between 0 and 2. And I think I've got that. There it is. So if I look at this line, which is the regression line, that's showing you what the average price per square foot is relative to the metro distance, where is it, getting the best fit? Really right in around here, because the distance between the line and the dots are pretty close. Not as good here, right? So when we're talking about something less than 1 mile away, it's not as good in its prediction. I've got, home price, and I've got price per square foot out here around 1,000 that this line is way off of. Where I don't have as many of that around the 1 to 2 mile category. Any ideas why that might be the case? Because this is going to lead up to the next kind of thoughts that we have for extending this regression.
Can you repeat the question?
Why do you think it's fitting better for properties that are between 1 and 2 miles than it is for properties that are between 0 and 1 mile? Any ideas? Any guesses? Well, one of the possibilities is that this includes data from both the DC metro area, the DC Maryland area, and the DC Virginia area. And if I live in Virginia and I work in DC, the distance to a metro stop would be important for my commute. Where if I live in DC, I would just end up probably doing what? Walking to work? Or, you know, it's just, I'm close enough that it doesn't matter. Is that making sense?
Yes.
Okay, so later today, what we're gonna do is we're going to see how adding a dummy variable around the geographical location of the property affects the result. So that we can take into consideration that people in Virginia or Maryland have a very different demand curve for housing close to a metro stop than say someone who lives in the DC metro area who might be able to walk to work, and so they're not as concerned. Okay? And that's, you would expect that, you know, if you live in Virginia or you live in Maryland, you're willing to get in your car and drive a little ways to get to a metro stop.
I have a quick
If you live in the DC area, you're probably saying, look, if you know, I'm willing to walk a mile to work, and it's not going to affect my demand for housing, and so the metro is irrelevant to me. All right.
Is it possible if Brian can make it so that we can download the slides on Canvas?
Yeah, you should be able to now. Oh,
Okay.
let me look.
They weren't on Canvas yet, Taylor?
The ones from last week are like, it has like the downloading thing next to it, but the slides from this week.
Can you grab those? Because you want to
It's
follow
on
along,
here.
right, Taylor?
If you just click it, it should automatically download.
Okay, thank you.
Yeah, should be there.
Click what, Shavai? The Canvas page?
The link, yeah.
It's a link on there, but it's no download. Usually it's a download button next to it, but it's no download button.
Oh, I gotcha.
But if you click it, it should still download.
Okay, it did. I don't know why it had a different name when I downloaded, that's why.
Thank you, Shavai.
All right, so let's come back to the results from the regression. Let's want to do it here. We talked about these numbers in the parentheses last week, and those are the standard errors that shows you how precisely the coefficient is being estimated. You can see in this case, the parameter is, you know, close to -90, and the standard error is 5.6. So relative to the magnitude of the coefficient, this standard error is pretty tight. And it's because of that the t-value is so big, causing it to have a very, very strong level of significance to reject the null hypothesis. And so you can see that the significance level is less than 0.1%. We've already asked this question, right? What do we do? What's our null hypothesis, and do we reject or fail to reject the null hypothesis? So the null hypothesis is that this m hat, which is this coefficient here, whether or not it's equal to 0 or not, whether or not metro distance has any explanatory value on the expected price per square feet in the data that we have here. And what did we conclude? What is Shavai told us that because of the 3 asterisks that we are rejecting the null hypothesis. And in this case, it's at a level of, this would be 10%, 5%, 1%. So the significance level here, you could go beyond, you could be smaller than 1%. And that's where I like this, because it shows you that the significance level could be nearly 0, because the t-value has a probability that's basically so far out in the tail of the distribution that I'm able to reject it at pretty much significance levels that are very, very, very close to 0.
So when we interpret it, would we say that the metro distance, like, is significant at the 0.01 level, or you said 99 point something? Which one, like, if we were trying to say in our paper we want?
I would just go off of here, because you as the researcher get to choose your significance level. And in this particular case, looking at your results, what's the lowest significance level that you can get away with? Well, according to the 3 stars, you can get away with, 1%.
Mhm.
And so if you can get away with 1%, why would you go to 10%?
Right.
Because it's saying that you have enough power, enough significance, you have enough information, statistical evidence to say that you are so confident that the chance of you making a mistake here is less than 1%. That's what it's saying. Why would you say that your confidence is less than that if you've got information that would say that you can make a higher state of inference with this 1% as opposed to 5%? Shivai, does that make sense?
Yeah, that makes sense.
Okay, so we would go ahead and we would reject our null hypothesis at a significance level of 1%. And that's just what we've got here in terms of the null, is that the coefficient is equal to 0 versus not equal to 0. Is it a one-sided or a two-sided null hypothesis?
I have a question again. I mean,
Okay, Brianna?
so is it always going to be between 0 and 1% where we're accepting or rejecting the null?
So your significance level is always going to be a small number. Because so somewhere between 10% and 0.1%. The more evidence you have against the null hypothesis here, the smaller that significance level is. You could have a significance level of, say, 50%, but would that make any sense? That means there's not enough evidence to reject the null. And that's why in our little table here, let me put it here. That's why in our table here, there's not even a, if it's 1%, there's nothing even out here, or even at, the 90th, this is 10%, but we generally want to have 5% or 1% or 0.1%. Very small chances where you're rejecting the null when the null is true. That's what the significance level is telling you. The chance of rejecting the null when the null is actually true. So I want to put a very low chance on that. And that's why the significance level here is actually very small. It's, in this case, it's 1%. So there is a 1% chance of me rejecting the null here when the null is actually true. Let that sink in and then see if that makes sense. Do you want me to repeat it, or is that understandable?
Just like summarize the last thing you just said.
Okay, let me kind of put it this way. How confident would you be in rejecting the null if the p-value or the probability of rejecting it when it's actually true was 20%? Versus how confident would you be in rejecting the null when the significance level for it is 1%? Would you be more confident at 20% or more confident at 1% rejecting the null, where that 20 versus 1% is the probability of rejecting the null when the null hypothesis is true? Which one gives you more confidence, the 20% or the 1%?
One.
The one. Now take that same, relationship between 20 and 1% and say the same thing about, okay, what about 1% versus 0.1%? Which one are you more confident in?
One.
1% would be, if that's the p-value is 1%, you have a 1% chance of having the null be true when it's actually, of rejecting the null when it's true, versus a 0.1% chance that the null is true, that you reject the null when the null is true. Which one are you more confident in? It would be the 0.1%. The smaller the number, the lower the chance of making a mistake. And that's what these asterisks are saying. The more asterisks you have, the more confidence you have that you're not making a mistake around rejecting the null. Because the asterisks are telling you what the chance of rejecting the null when the null is true. So you want that number as small as you can get because you don't want to make that mistake. Did that help, or should I go through it again?
I get it, but I think it's just gonna be a little bit of time to digest once I get into it, like in my own data set. Like I would just have to look at like a key. I think I just have to.
Yeah. It's so the significance level, the smaller the significance level, the more confident you are in rejecting the null. That's how I would put it. We kind of showed that graphically because if I come back here, that means the t-value in magnitude is bigger, which results in a smaller chance that you're making a mistake. We can go over that. There's a way to graphically see this, but I'd have to draw it, and I can't do that here online and make it very good for you to see and understand it. Okay. So in this particular case, so Taylor, can you in words, looking at this result here, for the coefficient on metro distance, tell me what that means about this null hypothesis.
That we will reject. It's significant, so we will reject the null hypothesis that it's not equal.
Yep. No, you'd reject that it is equal to 0.
Yeah, that is
Look.
equal. Oh, because the null hypothesis that's not.
Right, you're looking at the null hypothesis, and how confident are you about that conclusion around rejecting the null?
1%.
Right,
Oh, so 99% confident.
yes.
Yeah.
And the significance level there is 1%. Exactly. All right. So this is a way of just kind of giving you a rule for how to make a conclusion around the statistical significance of that null hypothesis. And so this is the null that the slope is not equal to 0. In other words, rejecting the null. And we do that if the p-value is less than 0.05. What would be your significance level using this rule?
Your significance level is 0.5. I mean, 0.6.
Right, so it'd be 5%, exactly. Okay, and so we would reject it, the null that the slope is 0, if the t statistic gives me a p-value less than 0.5. Okay, same thing goes with the intercept term. Okay, and we see that with the intercept term, that too shows that it's significantly different from 0. Meaning, in other words, that even a property that's right next to the metro station is going to have a price per square foot that's different from 0. Is that a meaningful hypothesis? Not really. I mean, that's not something you'd have to compare it to something else as say a house that is a mile away. But that's kind of why we're doing this is the linear model takes into consideration houses that are close to the metro station and say 2 miles away. So it captures all of that. So I don't really find in the regression this intercept term to be all that helpful in this particular context. Now later on, when we look at including dummy variables for the geographical location of the house, then that's when we're going to be asking the question about whether or not the intercepts are significant or not. Okay? Okay, so I think we've done all of this stuff. Don't really need to worry much about it because what we're finding is all the t statistics and t-tests are all done inside of R. The one thing is that if we look at this, a large estimate, in other words, in magnitude, the coefficient can be difficult to distinguish from 0 if an estimate is imprecise. When might it be imprecise? In other words, what would cause the standard error to be really big? And we talked a little bit about this.
An outlier?
Say again?
An outlier?
So the outlier?
Yeah.
Or I have a very small amount of data, right?
Yeah. A small data sample.
Yeah, exactly. And so I could get a really big value for the parameter, but I don't have enough data to be precise around it. And so in that case, I would not be able to reject the null because I don't have enough data to make that conclusion. And that's where it says, conversely, you can still reject the null for a small coefficient if the standard error is sufficiently small. And in that case, I got just tons of data. And so if I split up my data here and looked at it from, you know, those properties that are 4 or more miles away, as opposed to those properties that are within 2 miles, which one is going to have a more precise in terms of the standard error on the coefficient? Those that are over 4 miles away or those within 2 miles? Which one's going to have a more precise estimate of the coefficient?
The ones that are closer.
Yep. So the standard error on my coefficient that I estimate in my linear model is going to be very, very, very small for this part of the data that is homes less than 2 miles away from a metro station. Whereas I've got only a couple of handful of homes that are 4 miles or more away. And so I will have very little precision, statistical precision in my estimates here if I was just simply looking at a sample of those that are 4 miles or more away from the metro stop. And same thing with regards to just the inference. If you come and tell me, oh, well, what's your prediction for the price per square foot for a random house that's 4 miles away? Well, this is not going to be very accurate. There's going to be a lot of noise associated with it for if I just times this by 4, right? Because it's going to be go back to the regression. Sorry, there we go. Look, does this line do a very good job in explaining any of these homes that are 4 miles or more away?
No.
Basically, this guy only. All these guys, the line underestimates it. It's lowballing the home prices, not the home prices, but the price per square feet of homes that are 4 miles or more away from a metro stop. And so you have to be careful on how you use the regression results to make inference when you're working at a point in your data set that just doesn't have a lot of observations. Much better back here, on average, right? On average, sure, you got cases up here that are worse than, those that we found 4 miles or more away, but you also got a lot more that's doing better than what you saw on average, in the 2 or less miles away. All right, so let me jump back up and get here. Okay, so we've talked about statistical significance, but let's dwell on this question about economic significance. Okay? In other words, is it big enough to worry about? Now, coming back from an economic standpoint, whether or not it's going to be something that factors in to a person's economic decision. Now, when I look at this minus 87, that says that for every mile further away from the metro stop, the price per square foot drops by almost $90. Is that $90? We know that it's statistically significant. Is it economically significant? Shavai, what do you think? From your standpoint, if you're going out to rent and you find out that you're gonna have to pay $90 more for an apartment that is a mile closer to the metro stop, would that have an impact on your decision?
No.
Yes.
So I heard Shavai say yes. Did someone say no?
I said no.
Why? Is $90, do you worry about $90?
Well, in terms of rent, it's
Well,
not
yeah,
a big difference.
So if you're looking at 2 apartments and one is, say, 1,000 and another apartment is 1,100, would that factor into your decision? Because that's what we're saying here.
No.
I feel like it would. Like if you have a certain budget set aside for rent and that's over it, then
But in terms of metro distance,
I feel
Say
like,
that again, Tim.
oh, sorry.
but
No.
in terms of metro distance, like
So I guess from my standpoint, Taylor, you're willing to pay 100 extra bucks in rent to be a mile closer to the metro station. That's what that says.
okay, no. No.
No? And Shavai is saying,
I agree with Shavai now.
Brianna, where you fall on this?
I was gonna say I would get the apartment that's $100 less because
So, okay, so it is significant for you. So $100 is, and that's what we're trying to capture here, is it a big enough difference to a person in making their decision? And from my standpoint, $100, well, let me show you it this way. I think I've got a nice, this will help, look. So if I move a mile from a metro stop, that's gonna, it decreases the price by $50 per square foot. Okay? Now, on average, in this sample, a home is 1,600 square feet. Okay, and so a 1,600 square feet times by 50 is $80,000. So is $80,000 a significant amount, an economically significant amount of money to decide upon? And I think it is. So if I move a mile further down the street, I save $80,000 on my house. I think that that's something that would, so not only is this statistically significant, it's also economically significant. $80,000 is something that I think people would factor into their decision. And that's all we're saying here, is that even if you reject the null, it doesn't mean that it's still important from an economic standpoint. The number may be just so small, or maybe trivial in terms of your decision, that you just simply say, yeah, I know that I'm rejecting the null, that it doesn't have any, impact. But from my standpoint, from an economic standpoint, it doesn't. That's not, I don't think that that's what we're finding here. We're finding that moving further away is economically important in someone's decision. The question then is, are you gonna use the metro $80,000 more? Is it that valuable to you?
No.
So you'd probably say, hey, it doesn't bother me to be further away from the metro stop, because look, I'd rather take that $80,000 that I would have to pay to be closer to the metro stop and go buy a car, right? Because you could take that $80,000 and go buy the car and not have to ride the metro. So even though we found that it was statistically significant, you could come back and say, you have to ask yourself, well, does it matter from an economic standpoint? And as I point out in these bold letters here, it depends on the context, and it depends on the individual. And that's part of what you're trying to make clear in your project of where your judgment lands on this. And so just be, you know, in talking it out with others and explaining it and trying to get other people's views on this is really helpful. Because like we started with Shavai saying one thing and Taylor saying another, and then in the end they said, yeah, I think, you know, Shavai I would agree with Shavai. I mean, but again, this is economic significance. It's not a black and white outcome. It's very nuanced. Where with the statistical significance, it's black and white. You either reject the null or you can't reject the null, right? That's it. And it's very mechanical. Questions about that?
No.
All right.
Actually, do you want us to talk about the economics significance in our paper?
Well, you need to be mindful of that because in the end, that's probably more important than anything. Is if I'm looking at something like wages, and I got really big amounts of data, and I'm looking at two demographic groups, and there's only a very, you know, in terms of the coefficient or the difference between their means isn't all that big, but because I have so much data and so much precision around it, it says that it's statistically different from one another. But if the number is really small, you would say, yeah, we don't need to, you know, think about doing a program to take away this inequality if it's so small, even though it's statistically significant. If it's not economically different, then do we want to put all this time and effort and money into programs that could reduce that difference in their wages? So those are kind of questions you have to kind of ask yourself. And then depending upon what you come to find, you know, believe or conclude, share that in your project. And I will tell you next week in your presentation, those are the kind of questions that Brian and I will always be asking. And they may be new to you, they may not be, but I think that's where getting feedback is really helpful, because sometimes you just don't know it until someone asks you. So that's why I really find the presentations to be valuable, because it gives you an opportunity to hear from others that will give you, you know, thoughts on your project that you hadn't really been thinking about. And a lot of those are issues around economic significance, economic importance. You know, does it make a lot of, do the costs make sense given the benefits associated with it? So we'll talk it through, and I think it'll be clearer once we go through next week's presentations, and that's the feedback that you can then take and put into your report. All right. And we're still recording, so we're good, right? So all of a sudden I have this weird thing that I messed it up again. Okay. All right, this is the stuff that, you know, it's important, but really in the interest of time, let's spend our time on what's really going to be helpful. So, wanted to come, well, let me flip over here. Oh crap. So let me resume this, and then I'll show you something. Because we've been talking about this relationship about price per square feet, and distance from the metro. And we know, kind of looking at that data, that we had a lot of observations of properties that were within a mile, as opposed to not as many for those that were, 4+ miles away. So what I wanted to do is to plot the data where we're gonna look at it relative to its location. Does that come out okay for you guys?
Yes.
Okay. So over here is the legend, and it shows you each observation's location, depending upon the circle, triangle, or square. And if I look out at those properties that are 4 miles or more away from the metro stop, where are they all geographically located? I'm trying to remember, was it Taylor? Didn't you live in, I can't remember who it was that lived in like College Park or something like that. Was it, or Springs, what is it called?
Sandy Springs?
No, the Springs area of DC in Maryland.
Silver Spring.
So Taylor, the DC area,
Yeah.
okay? Are you surprised by these triangles out here in the data set? Or does that kind of go with what you would have expected?
The triangles are saying that it's gonna get cheaper the further it is away from the metro.
No, just think about it from the data standpoint. Don't think about it from
like
the
the
regression
price.
standpoint.
The price
Just
of the
think-
home.
Right, so the price per square foot, or don't even worry about the price per square feet. Let's just think about the metro distance. Because that's what I keep saying is I say, oh, here are observations that are 4 or more miles away from the metro. Is that surprising that all of these, that let me ask you this, is it surprising to you that there's no DC properties out here?
No, because all of their houses are close to the metro.
Exactly. So in my sample, all of the properties that are at 4 miles or more away from the metro are all located in Maryland. In fact, I can almost conclude that every property in my sample, in my data set, that's 3 or more miles away from a metro stop is located in what area?
Maryland.
Maryland. So maybe it makes sense to treat those differently than those in the DC or Maryland, or excuse me, DC or Virginia areas. Because they're on, for the most part, have quite a distance between the property and the metro stop. Do you see, it's kind of hard for me to see, but do you see many Maryland properties in this area down here, say 2 miles or less? What would you conclude? What geographical location seems to be dominating for properties that are, say, 1 mile or less?
DC.
Taylor, I mean, so Taylor, you said DC. Is that what others are saying?
Yeah, I said DC as well.
Yes.
Yeah, and it makes sense, doesn't it?
Yes.
If you're in the metro DC area, you're probably pretty close to one of the subway stops. And then when we move into Virginia, you see that, you get not quite as many, they're kind of in between the Marylands and the DCs. So, and so when I look at this, I would kind of say, hey, maybe geographical location is something that I should factor in to my analysis to deal with price per square foot, because of its relationship with the metro, is going to be affected by the distance. If I've got a particular geographical area that's closer, as opposed like DC, as opposed to further away like Maryland, let's see if we can use that information to make better inference about the price per square feet's relationship with the metro distance. And you can see this in other contexts where I could be looking at, women's wages as opposed contrasted with, men's wages. I break that sample up and bring in a dummy variable that would take into consideration that, maybe that women's wages on average are less than men wages. And I shouldn't be mixing apples and oranges here. I need to treat them separately. Well, here my apples and oranges are the geographical locations. All right, so let me get down to this. And that's really what's coming up here. Are there other factors besides the distance to the metro stop, like location, that are going to be relevant and important to look at? Now, I just showed you a scatter diagram, and just looking at the scatter diagram, would you conclude that location should be a relevant factor or not?
Yes.
So let's see how we can do that. How many of you are familiar with dummy variables?
I am.
Yeah, we used it before.
You've all done dummy variables, right?
Yes.
And so a dummy variable in this context is going to allow for the regression to treat the mean of those properties in each of the geographical areas differently. Okay, that's what it's going to allow. And in fact, we kind of show it this way. We've been looking at metro distance, but what about price per square feet? Because that's the dependent variable. Do you see any kind of clustering like we did with the metro distance, but now with regards to price per square feet and the geographical location? What geographical location is dominating those properties that have a price per square feet of $750 or more?
DC.
DC? Okay. And so what we're gonna do is we're gonna allow for the price per square feet to be different. The average price per square feet to be different for the DC versus the Maryland versus the Virginia geographical locations. And we're going to do that by using that state variable to create dummy variables around that. So we're going to do a little bit of a review so that we completely understand what that means, so that you can then interpret what the coefficients from my linear regression on those state factor variables mean, and whether or not they're statistically significant or not, okay? Now, through this whole process, we are not allowing the relationship between price per square feet and the distance to a metro area to be different for the geographical location. We're just letting the average price per square feet to be different based upon the geographical location of the property. So the slope coefficient is going to be the same for all three geographical locations. We're not gonna, we could play with that a little bit, we could make it, different for them, but in the context of what we're doing here, let's just say it's beyond the scope. But it's very easy and very doable, but we're just not gonna cover it today. All right, and so graphically, this is what we see thus far. This was our fitted line showing what the on average level of price per square foot was for distance away from a metro station. And that's where we got. And what we're going to do is now we're gonna allow the average to be different for, well, I said average, but what I'm really saying is I'm gonna allow the intercept, which is that coefficient, to be different if the observations came from DC versus Maryland versus Virginia. And that's what we see over here. So this first solid line, that it has the highest intercept, followed by Virginia, followed by Maryland. Now, as I said, the slopes are the same, and so I'm gonna show you how we can estimate these lines, what the estimates were that generated these lines. But let me ask you this off the top of your head and whether or not it's even possible. There's not a lot of difference between the intercept for Virginia compared to DC. Can you tell me, or do you even think that there's a statistically significant difference between the intercept term for DC versus Virginia? And that's the question that we need to ask and answer. And then the same thing about, well, what about Maryland? Is this intercept here statistically significantly different from these two? And we'll find out whether or not we can address those questions, okay? And that's kind of where we're trying to work towards, okay? All right, so let me think how I want to do this. Yeah. So this is just simply a regression. Let me show you what it is. I don't even think I have it here. Where I'm regressing price per square feet on the dummy variables. And I don't include a constant. I don't include an intercept. And here I do an intercept. And so the constant is $451 per square feet. And notice that the average price per square feet in DC is the same. And so when I look at this coefficient here, this minus 49.97 for the dummy variable for Virginia, whether or not the property was in Virginia, do either of you know, or can you give me an intuitive explanation for what this number means? This minus 49.97. Okay, silence tells me no, so let me go. Look over here.
What? I'm not understanding the without.
Yeah, so that's why let me explain it this way. The average price per square feet in DC is $451. That's the same thing I get here if I do a regression on those state dummy variables, but with no intercept term. I get 451, I get $321 average for Maryland, I get $401 price per square feet for Virginia properties. So these are the average price per square feet of those homes in DC, in Maryland, in Virginia, okay?
So the constant is a representation of DC.
Exactly.
Okay.
What about this number? So if 451 is the average for DC,
Oh, if you're in Virginia, your house will be $50 less.
$50 less than,
The intercept, which is DC.
which is DC. What about the 129?
Your house would be $129 less than DC.
Than DC. So in this particular case, what is the base geographical area that I'm comparing everything to?
DC.
DC. And so when I interpret these coefficients, they're always relative to the base, which in this case is DC. Now, remember we looked at these factor questions a month and a half ago. Do you remember how R treated factors? Which one it would make the base? Any recollection? In other words, why is R going to use DC as the base reference here in the dummy variable case? We answered this briefly, like I said, probably 2 months ago.
It's more representative. There's more representation.
It's alphabetical.
Oh.
So that's the state variable. Let me just do it here. I'm gonna do tail. I'm getting arthritis in my fingers. And we're gonna use join, whoops. Okay. So MD, okay, let's do this, unique. Oops, sorry. Okay, do you see that? Or is it too far down? So my state variable in my data is denoted by Virginia, Maryland, and DC. Okay, and they're factors. And the way that R looks at this is it says, okay, I'm going to order them in alphabetical order. And since DC is at the beginning of the alphabet, it gets treated first. Since Virginia is at the end, it's treated last. And so the way that my results are going to be ordered when I use this in my regression is that the first one in my factors is going to be the base, and in this case it's going to be DC, followed by Maryland, followed by Virginia, because it's ordered alphabetically. And that's why I set it up this way. Is that the base is going to be DC, and you can see that as we're comparing the numbers here. And then the other intercepts are going to be values in relationship to the base, as Taylor's explained and rightly got exactly right when she said, oh, well, all I have to do to get to Virginia's average price per square feet is to take 50 off of this 451, and I'm getting to Virginia's actual mean. And same thing with the state of Maryland. I take 130 off of 451 and I come up with this 321. Okay, any questions about that?
No.
Okay, good. Do you guys want to take a little break before we get into some equations?
Yes.
Yeah, I think me too. All right, so let's start back up at 10:45. All right?
Thank
Okay.
you.
And Brianna, remind me to start the recording again.
Will do.
Thank you.
I might give you this. Is a gender neutral.
Brianna, do I got
I'm
you?
here.
Oh, good, okay. I started the recording, okay? All right, any questions that came to mind during the break?
No.
Okay, good. So this equation should look familiar to you. This is the linear model that we've been working on. So we've looked at price per square foot this morning and its relationship to the metro distance. And then we had an intercept term. And we saw that we've done that regression. And so what we're gonna do now is, like I said, we're gonna include the geographical location into our regression that allows the intercept term to be different depending upon where that property is located. And in this particular case, we're letting the base group be DC, and so this coefficient here, B1, which isn't associated with any group. Notice I'm not multiplying it by DC's dummy variable. It's just sitting there by itself. But that coefficient B1 is going to be that intercept term for those properties in the DC area. The coefficient for B2 are associated with the properties in Maryland, and those in B3, the coefficient B3 are associated with those in Virginia. And notice that it's alphabetical. This was DC, starting with D, M, and VA, and so that's the way that we keep track of the fact that the state variable are characters with DC, MD, and VA, and how the linear model function is going to treat that variable when it goes ahead and does the regression. Okay? And then what we need to do is we need to understand what this B2 coefficient means and what this B3 coefficient means. And it's all based upon the B1 variable. Very similar to what we've already talked about. And so, because B1 is for DC and DC is our base group, B2 is going to be how Maryland's intercept differs from the base, DC. And so if I add these two together, that would B1 and B2, that would then tell me what Maryland's intercept for its properties would be, like we saw before we went to break. And that B3 plus B1 would then be the same thing, but for those properties in Virginia. And so that's kind of what we're saying down here, is that if I look at this, the equation here and look at the parameter estimates and things like that, I can then infer what the price per square foot for properties in DC by just simply taking what's common to all of them, this M times metro distance. For DC, all I have to do is add in the B1. For Maryland, I not only include the B1, but I have to add in the B2. And that Virginia, I add in the B3. But I can't just, for Maryland, look at B2. I've got to use the base because it's the B2 is just telling me how Maryland is different from the base, which is DC. B3 is telling me how Virginia is different from the base, in other words, DC. Does that make sense? And in this case, all of them have the same relationship relative to the metro distance. So are we ready to jump into this and see what it looks like? So let me show you how we do that regression. Let me start this back up. And all I have to do is include that state variable in my regression now. And I've already typed it in here, so it's here starting on line 110. So I can see it. And so I'm gonna execute the command LM where the dependent variable is price per square feet, and it's gonna be regressed on metro distance like we always have done thus far. But now I put a plus sign because I'm going to include an additional variable. And in this case, it's that variable that captures the geographical location of the property that's got the variable name state, and then I just put in the data set that I'm using. Okay, so let me go ahead and run that. And that executed, and now let's see what that looks like, the regression results. So let me bring that up. Okay. All right, so does anyone want to give a crack at it in terms of telling me what's going on here? I guess we should start with the metro distance. Anyone have an idea what this is? How would you verbally describe what that minus 74 means, or what interpretation you would give it? Shavai?
I would say that
Do you want me to go back to the equation?
yes.
Okay, so that's minus 74 is the estimate for M1. And that M1 is the same for every single metropolitan area in my sample. So since that M1 is minus 74, looking at this, what would you say? For every additional mile away from a metro station, what would happen to the price per square feet in either DC, Maryland, or Virginia?
In DC, it would decrease by $74.
Yeah. Is it any different in any of these other metro areas?
Like the actual number is different.
No, it's the M1.
Oh no, the M1 is the same.
No, because in this particular case, we're saying that the relationship between the square price per square foot and metro distance is not being affected by the geographical location of the property. That may be right, it may be wrong, but that's what we're assuming. Okay, that's where is it? I don't know where we said it. Yeah, we still assume the slopes are the same for each state. That's what it says. So that coefficient of minus 74 is the same for each state. Now, I think it was Brianna that asked me the question. For M1, this minus 74, can you reject or not reject that it's statistically significant, and given the answer to that, at what significance level? So can you reject the null or can you not reject the null? That the coefficient on Metro, this M1, is equal to 0. Reject or not reject? This is for you, Brianna.
I'm gonna say, 'cause I still struggle.
Does anyone want to help her out?
It is significant, so we would,
Fail to reject.
It is significant.
Oh.
How did you, before I go to the next step, Shavai, you're right, it is significant. And how are you figuring that out, Shavai?
the stars on the right is 3 stars, so it's significant at the 1% level.
Yep. Because the p-value associated with this thing is nearly 0. So we know it's significant, and if it's significant, we would then reject the null hypothesis.
Okay. See, I said it, but then I second guessed it because it was silence.
Because the t value here is an absolute value very big. So it's giving you a lot of information against the null. Now compare that, okay, so are we okay with that? Is there now Shavai, you said at the 1% level, right?
Yes.
That's the significance level. Is that the smallest that we can go here? Because look, the p-value is tiny. So we could actually go down to the, instead of just the 1% significance level, we could go down to the 0.1%. So there's plenty of information here, statistical information here, to say that this coefficient is different from 0. That is significantly different from 0. Taylor, anything that we're missing here, or is that pretty much you're in agreement?
I agree with you.
One other thing is look at the standard error of this thing. Whoops. It's 6.37, and the Metro coefficient is 74. That number's small relative to the coefficient, and that's what's leading to such a big t-value here. So there's plenty of information here that's telling us that I can reject that there's no relationship between the price per square feet and Metro distance. Same thing as what we saw before. So everything there continues to hold. Right? Now let's go to the next step. Okay. What does this intercept mean? And which geographical area is this intercept relevant for? Let's go backwards. Let's start with Taylor. What does this mean, and who is it for?
This means that the pricing of the houses is estimated to be $496.
Okay, and for which houses?
The houses within DC.
Okay, exactly. Because I use the state variable here in my regression, I know that this intercept, because DC is the first alphabetically in this variable, in the variable state, it shows up here. So this intercept is for the DC area. So for, on average, the price per square feet of a property in the DC area that's sitting right next door to the metro would be $496 per square feet. Is that significant? Is it statistically significant in the sense that I have a null that says that it's equal to 0? Is it significant? In other words, can I reject the null that the average price per square feet of a property in DC right next door to the metro is 0? Brianna, I'm coming back to you because that's the same question I asked you before, but for the coefficient. So how would you answer this one?
Yes, you can reject the no.
Okay, and Shavai, what's the significance level that you can reject it at?
You can reject it at 0.01.
Yep. Okay, so we know that. Now the next question is, what about this coefficient for the state of Maryland? This minus 56. Brianna, what do you think that coefficient, how would you interpret that coefficient of minus 56?
Negative, so
Let's do this. Here it is.
mhm,
The B1
mhm,
would be the 496,
uh-huh,
and the B2
mhm.
is the minus 56.
Okay,
So, okay,
so be positive actually when you calculate it. So, the estimate would be like around like 440.
yep. So what does that 440 apply to?
Um, the the distance away.
No, it's an intercept.
Oh,
So it's
is that the price
average
per square footage?
the average price square footage of
Oh, Maryland.
those in Maryland.
Okay.
Now here's the one for you, Taylor.
I have a question.
Okay, Shavai, go ahead.
Okay, I'm kind of confused. You said 440. I mean, do you subtract the 56 from the intercept?
Yep.
Okay.
I'm just taking the 496 and adding it to the minus 56. And because that minus 56 takes away from the 496, that's where Brianna came up with the 440.
Oh, okay.
Okay? And that's what this equation here is telling me.
Okay.
For Maryland, I'm taking the estimate of the intercept and the estimate for the indicator variable for Maryland, adding them together to then come up with what the average price per square footage is for a house in Maryland.
Oh, okay. Makes sense.
Does that make sense?
Yes.
Okay, now Taylor, here's the next question.
Mhm.
Are homes on average in Maryland? Let me back up. Is the price per square footage of a home in Maryland statistically different from a home in DC?
Yes.
And how are you coming to that conclusion?
Because Maryland has a negative. Well, they're showing a price difference, and then they're at the 1% level also. But Virginia's not, so I don't think their price is significant at this.
Okay, now can you explain to Shavai and Brianna How are you making that kind of determination? Because you said it's significant that that the expected price per square feet in Maryland is significantly different from that in DC. And the way that you determined that was you looked at the 3 asterisks, you looked at the p-value, and you've concluded that at least the 1% significance level, you can reject the null that they're equal. In other words, you reject the null that this thing's equal to 0, right? Because if they were the same expected price per square feet in Maryland and in DC, this thing would be close to 0 and it would not be significant. But for Virginia, you're saying that the expected price per square feet of a property in Virginia is on average no different than that of a property in DC. Because this -10, even though it may sound like $10, right? That's what it is. The uncertainty around it is 12, which means that it has a p-value that's 0.37. And so if you rejected the null here, that they were the average price per square feet of Virginia and being different from DC, you would be on average wrong 37% of the time. And you don't wanna, that's a lot of risk to take on. These things are close to 0. Here it would be saying that you'd be wrong 37% of the time. That doesn't sound like a good bet. That doesn't sound like strong inference. That doesn't sound like statistical significance. And so as Taylor said, you cannot reject the null that the average price per square feet in Virginia is equal to the price per square feet in DC. Now, looking at the data, I don't find that very surprising because you said before that a lot of the data in Virginia and DC look alike, not so much for Maryland. So let's pause there and make sure you understand why Taylor was able to make those, why her statistical inference makes sense. Notice we've got the 3 asterisks here on the intercept, on the slope coefficient, and on the state indicated variable for Maryland. We don't have it there for Maryland. We don't have it for Virginia. So we know that this is not significantly different from 0. And if it's not significantly different from 0, that's meaning that it's not different from DC. Because everything on these intercept coefficients is relative to the average price per square feet in the DC area. Does it make sense? So how can I see this graphically? Comes back to this. The slopes are the same. The intercepts are different, but they're so similar between DC and Virginia that you cannot reject that they're equal. Where for Maryland, the vertical distance between the two is big enough and precise enough to allow me to reject that they are the same. In other words, that that Maryland and DC are the same. Making sense? And this is another way of seeing it when we just put it into a table. Here's the one for DC. Virginia is basically $11 cheaper price per square feet. But notice there's no asterisks here, and the standard errors are quite big relative to the actual parameter values. The standard error for Maryland is the same as the standard error for Virginia, but the coefficient is so much, it's 5 times as big. And so it's far enough away from zero that it's significant. And I can say that the properties in Maryland have on average are having lower price per square feet. Okay. Any questions about that? I think these are just other ways that I've reported them, okay? So we know what the base group is, it's DC. We've talked about how R chooses the base group, it's alphabetical. And we've also explained what those intercept terms for the Maryland and Virginia mean, and it's all relative to the base group DC. And so everything that you've done thus far in your inference is being based upon these values here. And everyone was getting it the way that it should be in terms of talking about the statistical significance of the average price per square feet in Maryland, Virginia relative to DC. I think we're all pretty much in agreement here. So here's another way of looking at it. What do you think is causing the intercept for Maryland to be lower than that in DC and Virginia? Where in my data, what in my data causes me to think that that's going on? Some of it has to do with this stuff out here. But if you look, all these little triangles are down in here too, which are properties in Maryland. I wonder for those who've lived in the DC area, whether or not this is intuitive, that this is what they would expect. I haven't, but my general perception has always been that Maryland is a little bit more affordable than Virginia is, or even DC, for the average home. Not quite sure why that is, but you know, whether or not it's convenience to DC or whether or not it's harder to get into DC, just seems like property is a little bit cheaper in Maryland as opposed to Virginia, and that would explain this. If in your own research you're not happy with the base, in other words, if we wanted a different baseline than DC, we could come in here and we change the factor, and in this particular case, we want Maryland to be the base. And so we'd use this RE-lev, using as factor on the state, and then we let the reference be MD. If we wanted it to be Virginia, then we just change this to VA. And then my coefficient results look like this, okay? And so, can anyone tell me what this intercept term means, given this regression? Taylor?
Yes. So the first state is, oh, reference state is Maryland. So the price of the homes in Maryland are on average around $440.
Yep, great. And then this coefficient here, this minus 74, would then be how much, oh, excuse me, that's for the metro, sorry. This value 56.35 would tell me how much that average per square foot in DC differs from Maryland. And so because it's positive, I know that DC is more expensive than Maryland by $56.35 per square foot. Now, I don't have my significance level here, but going back to what you knew and saw before, what would you expect? Would you expect this to be significantly different or not? There's Maryland, there's DC. And so the significance here will not change by changing the reference. And you can see the same thing here, so I wish I had that, but I don't. Okay. Guess we could run that. Do you want to run it? Let me go ahead and run that code. We'll see what we get. Okay, so this is whoops. Dummy variable with state where Maryland is base. Okay, so OLS2 dummy LM is price per square foot tilde metro distance plus, this is where I have to change it up. And in my case, I'm going to use the same thing, joined data. Whoops. Let me run that. Oh, typing is bad. Tour and okay, so let me go ahead and do summary. OLS2 dummy. Do that. All right, so let's look at it. Whoops. So now the base is Maryland, so we get 440 for it. It's statistically significantly different from 0. The significance level is less than 1%. All we've changed is the ordering of the dummy variables, so nothing with regards to the coefficient on the metro distance is going to be affected. And if I look at the relevant factor for the intercept for DC now, it's 56. And the part that's a little puzzling to me is why we're getting significantly difference between Virginia and Maryland. I wouldn't have expected that. So I'm a little puzzled. I need to think about that. Do you know why I'm puzzled or what might be creating that question in the back of my head?
Is it? Oh no, never mind.
Nothing's really changed. I just changed the order. That's all I did. And yet, look at my look at my standard errors. Okay, and let's come back here, the standard errors again, especially for the intercept terms. And so I'm a little surprised they've changed. They shouldn't have changed all that much. The one that's a little puzzling to me is this DC one. I would have thought that it would have been, you come back up here, look how small this one was. And then how big, you know, twice as big up here. So, but you can see here, yeah, they're all significant, but Maryland relative to Virginia is only significant at the point, is only significant at the 1% level and not at the 0.1%. We're not finding that up here. So that's why I'm a little puzzled. I have to think about that a little bit harder and figure out why we're coming up with different results. Because all I've done is changed it. I don't think Brian is listening, but he may have an idea, but I don't think.
Why, oh, why would reordering the factoring cause?
Yeah, because all I've done is ordered the matrix in a different way. It shouldn't change anything. So I'll have to do a little bit of homework on that.
Well, it's relative to Maryland, right? So.
It shouldn't matter. It's just
Yeah, but-
differences.
Oh.
Why would the standard errors change? That's the problem. So, because these values didn't change. Okay, so let's do this. Why am I not getting? Because I moved it. There we go. All right, so I don't like doing breakout sessions virtually because I can't help you as much. I can't see your screens, things like that. And so this one is just basically one that you should do on your own, which is really just going over what we did today in this last part about indicator variables for with regards to the state indicator variable. And then what I haven't done here is I haven't produced the results into state Stargazer. And the reason why I haven't done that here is because I'm working within an R script and not within an R markdown. So you know, Stargazer in the R script would give me a bunch of garbly code, but in R markdown, Stargazer gives me things that look like that. Okay, so what that breakout session basically is asking you to produce a table like this using Stargazer. And the script file that you have from today's lecture will help you through that. And then most important isn't just, you know, producing the regression table, but it's being able to write and explain what it tells you about the predicted price per square foot for those in DC versus Maryland versus Virginia, okay? And notice in one case it's asking on top, and in another case it's asking for a square foot. Now this is the predicted, it's not talking about significance. It's not asking you to make any inference around the null hypothesis. This is just simply around what you expect the price per square foot to be in the different DC areas. So the next thing that you should do is, once you answer those two, answer the question about whether or not there's significant differences between, you know, the predicted price square foot of a metro, of a property right on top of the metro in DC versus Maryland versus Virginia. And then what that significance level would be, okay? And there's, in the lecture code, you can find the data, or excuse me, this is how you would basically do that. I think it's more important that you go through this, but then you answer these questions along with the statistical significance questions that I just verbally shared with you. Okay. Any questions? That went quicker than I thought it would be. Go ahead, Brianna.
Are there any one-on-one office hours available for this week?
Yes, there are. If you want to just email me or Brian, we can set something up.
Yeah, if it's possible,
Sure.
can I do like 2 meetups before the actual
Before the presentation?
yes, please.
However you need.
Okay.
So let us know your times.
You
I'm
can
gonna
do one
send-
with Brian and you can do one with me.
Okay, that
Just
sounds
let us
good.
know.
Hmm?
You know,
Alright,
reach
I'll
out.
send you guys an email right now.
Cool.
So,
Okay.
Will we be getting feedback on our first draft before the presentation or no?
Feedback on your first draft? Sure. I'm gonna be looking at those on Tuesday and Wednesdays. Is that early enough?
yeah.
Any feedback before Friday would be good, I would expect, right?
Yeah.
Yeah, I'll do that.
And just to clarify, we present on Friday.
Correct.
Okay.
So 15-minute-ish with, say, what we would do is 10-minute presentation, 5 minutes of discussion intermixed. That would be the time frame that I would aim for.
So if we didn't incorporate regressions in our draft, can we incorporate it in our final paper?
Sure, sure. And you get kind of, you know, like I said early in the semester, degree of difficulty. So that would boost you up in terms of, you know, the degree of difficulty and then the points associated with it. So, and Brian or I would be happy to talk it through. It honestly, it shouldn't be that difficult to incorporate a regression into a lot of your work. I know that Brianna's work has it. I'm pretty sure that Shavai has it. So, Taylor, I think it would be probably easy for, you know, relevant for your question too.
All right.
Okay? All right, well, I'll let you start your day earlier at 11:30 rather than 12. And yeah, if any, you know, Brianna, we'll get your email and set you up. Anyone else, please reach out. We'll post this video. Shavai?
I need extra office hours too, because I need to, I need help.
Okay,
So I can email you all.
just email Brian and me and we'll set thing up. And
Okay.
also, Shavai, Lauren is also someone if she's unable to, you know, just exhaust all your resources between Brian, me, and Lauren. We're here. Same thing for the rest of you. See if your project buddy in terms of like Taylor, you could have Michael help or something, but we're also here. Okay.
So if we send an email, should we send it to the econ 345 email or like your regular email?
You just CC that address just so we can have that's like a kind of a common record of it, because it's easy for if you're emailing one of us individually, it's easy for the emails to get siloed.
Yeah, send it to my Fed address. And that way, it's not gonna get lost in all the other stuff. And then I can set up an individual time on Zoom to meet, okay?
Thank you.
All right, any other questions or requests?
No.
All right, well, I look forward to next week. This is gonna be exciting. I'm really excited to see what you guys, what you've found and what you've done, and to ask you some questions and give you some feedback, okay?
Sounds good.
All right, well, have a good weekend and we'll see you next week or
You
before then,
too.
okay?
You
All
too.
right.
See you on next week. Bye bye.